Hey everyone, how you doing? So this is without the mask. I'm getting furry. What we're going to do is we're going to look at your MATLAB code for second orders, and we're going to develop what will be a technique that will help us get through this. So bear with me here as I switch over to Blackboard and hopefully, or not Blackboard, a blackboard, so that I can write out here. So we're going to look at our spring systems, and so we're going to have a generic spring system, and I'll do the same thing I did before. I'm going to write this in. We'll make it the spring's amplitude is moving within the x position, and it's changing over time. Yeah. And that's x, and we'll have some function of x, and even possibly t at some point. That can be a driving function. Right? The function itself can change at time, can change with position. It's a fully variable function. Now, we're going to do some things here to look at how we can simplify the system, how we can make the system kind of collapse down into a first order. So the first thing we're going to look at here is we're going to look at a change of variables. And so I know a lot of you don't like the dot notation, but I'm going to show you why the dot notation is going to be useful for us here. And we're going to put some things out to the side that might help us. So if I make this x double dot plus b x dot plus kx, I'm holding information about, I know these are all time derivatives. Now what I'm going to suggest next is that we do a variable substitution. Now in the old notation I would have said that y is equal to dx dt, which means dy dt is equal to second derivative of y with respect to, or dx, sorry. And this let us have a substitution where we can only be talking in terms of first order differentials. But this can get cumbersome. The trick we are going to aim for in all of this is we're going to be able to set up equations in dy dt and in dx dt. And if we can set up a system of differential equations like this, I can divide this differential by this differential. So that'll give me dy dt over dx dt. But oddly enough, that's going to give me dy dx. And so x and y will have meanings within the slope fields that they generate. And that's going to be our goal, is to generate slope fields that will have meanings. Now t vanishes from the differential word, right? But it's still there, and we're going to have to take care of it. Now this is some cumbersome notation. So what I'm going to do here is I'm going to introduce the notation that y equals x dot. Therefore y dot is x double dot. It's just an easier way of carrying this notation about for us. And I'm going to write this equation now. I want to solve it for x double dot. So I'm going to bring this down here. And since I'll focus on this, I'll rewrite it as I focus on it. So I'll divide everything by m. And so we have everything in terms of accelerations now, right? Because if force divided by m is an acceleration. And now I will solve, so x double dot is equal to my driving function divided by m minus b over m x dot minus k over m x. But x double dot is y dot from our substitution up here. And so I'm going to have my driving function minus, well, x dot is y minus km x. And so I've taken this differential and have it in terms of variables. It's going to be plottable. I'm going to be able to make an xy plot, which will be position versus velocity in a standard spring system. And then in the dots will tell me a stream field, a vector field, is our goal here. So if I bring my system of equations together, I have x dot equals y, and I have y dot equals my driving function over m minus b sub m y minus k sub n x. And so there we have our differentials that we're going to use. Now what we want to do is when we plot this, we can think about each element here can be a full-out vector. The slope will be my change in my y over my change in my x. And if I keep the sign information, it will point in the direction things flow. And so I can look at a motion in my system as it's working its way towards an equilibrium. And we can make a plot. And I'm going to do an x dot versus y dot plot, I think, will be the first thing. Right? Because dx is x dots, dy's are y dots. And I can make my way through and make a grid of these values that come about. So let's work on computationally doing this. So these are the two things that we need to do in MATLAB. So I'm going to switch over to MATLAB here, hopefully, and then we'll use this to build some things. There's some geometries we'll have to keep in mind here. Alright, so in MATLAB here, we're going to set up some space for our functions. So we're going to keep a variable for mass, a variable for our drag coefficient, and a variable for our spring constant. And we're going to have a place for a driving force. For right now I'm going to make the driving force 0. And so we can now set up the equations for our variables. So the first thing is we're going to plot this on a grid. So I'm going to look at plotting this on a mesh grid for my x and y values. And so we're going to work on all the x and y values. So let's see here. So I'm going to say that x comma y will be a mesh grid. And I'm going to go from -5 in steps of 0.25 to +5, and from -5, oops, let me keep my decimals in here. In steps of 0.25 to 5.0. So we have a mesh grid that should be able to walk us through. And what we'll want to calculate is our derivatives. So x dot was equal to y. Let me put semicolon 0, we'll get a lot of stuff printed out. And y dot is going to be our driving function minus, what was it? It was b divided by m times y minus k divided by m times x. Okay. Let's see here. If we go back, I think that matches our equations fairly nicely. So let's look at our, oh, there they are. Right. Let me see if I can point to the, how am I? Right here? Right? There's x is y, y dot is f minus b minus m y minus k minus x. And is that what MATLAB is showing us here? Let's see. F minus b divided by m, y, again, b right here, b divided by m, y, and minus k divided by m. Yeah, so we're good. So we do have our ability here. I like this. This is neat. This is my like silly space, right? Fortunately, like I have to, look through different things, but we're good with that. All right. And so let's get back here and get this mesh grid going. And let's see. Whoops. I'm gonna come here. Mesh grid's parentheses, right? Now the first thing I'm going to do is I'm going to print a quiver object. X dot, comma, y dot, comma, what do I want to do? No, I want to do my x and my y, and I want them, for right now, I'm going to have the end of the vector at x dot, y dot. And let's see if I typed in any bad errors on there. Yep, invalid operator. Where did I invalidate the operator? Oh, yep, my dot's on the wrong side there. And I have a phase plot. Let's see if we can get the phase plot to show up in OBS here. Give me a second, I'll put myself on camera. Ooh. Or we can do mixed mode. I'll use this. I use this more in other teaching demos. It's weird. I have to do the whole, meteorology thing to point out to my equations. I have a black drape that goes behind me, and it works really nice when I do that. But anyway, that's not what I'm trying to do here. What I'm going to try to do is I'm going to try to get another window for you here and pull up the figure. There it is. And so there we have the phase plot. So notice we have the direction that our velocities and accelerations should be going into. They're mapped out nicely for all points. So for any point in space, I have the direction this will flow. But the vectors are kind of small. So we have to do something to get the vector size to work for us. So let's try to fix that and get our vector scaling to work for us. So I'll come back in here and we'll make a vector scaling. Make the vector scaling work. So I know that I can give myself a u. I can make an angle, right? So I can make some angle that is going to be the arctangent of y dot divided by x dot. I think that'll work. And then I can make a u vector equal cosine of angle, and a v vector is the sine of the angle. Now what I've done is I have made these so that they're going to be unit length. Because I'm not multiplying anything out in front of them, they have a unit length. The cosine component of this vector will equal this 1 squared plus the sine component of this vector will equal 1. And so this does make a unit length. And so let me run this and see what happens to my quiver. And so we'll pull over here and we'll go to the figure. This is better. The arrows are larger. And if I come back in here and I look at this figure, I've got unit length arrows and it's telling me what happens, but this pattern was swirling in completely before. Now the arrows in the lower half are going in the wrong direction. Right? And so We want to fix that. So for some reason, everything in the upper two quadrants is fine. Everything in the lower two quadrants isn't. In fact, if let's look at our function here. Let me get over blackboard. Pause for a second here. Let's get over to the blackboard. I want to think for a second of what's happening in our space. So what we've done is we have the direction vectors that things could be going about. But we're trying to figure out how to plot them. And so in our direction vectors, we're using the idea that x dot is equal to y, and y dot is equal to our function. And when we did this, we used a tangent function, an arctangent function, where we did y dot over x dot to get the angle that our thing would be at. And so the angle that our object would be at, well, we have this problem as tangents only good from 0 to pi. From pi to pi, we get repeated values. They're not clean functions. And we've lost information about the signs. Now we can, if we look at our figure, which I'm going to dance back to here, that we generated, which I think is here, we can see that the upper quadrants are fine. The arrows point in the wrong direction. Well, it looks like our lower quadrants, the arrows are pointing in the opposite directions. We've lost all sign information down below. And that's the nature of having a arctangent function. We only get good sign information. So what we need to do is somehow just get the sign of the vector. And so this vector here is going to be, well, it's the x position plus some change in x dot. And it's the y position plus some change due to y dot. Okay. And so the vector moves out. And so if these were getting the signs correct, when we use the angle on them, then these signs are working. Well, what happens? When we're up here, y is positive. And when we're here, well, right, the thing talking about the change in x is always positive because y is always positive, right? If we look at the differential equation in the upper two quadrants, all changes in x will always be positive because the y value is positive. Now, if I'm in the lower quadrant, all changes in x should be negative. When I'm here, right, then y being positive, then for positive values of x, I get bigger negative numbers, and for negative values of x, I get positive numbers. Whoops, didn't mean to do that. Let me reposition that back to where it was. So that's the geometry I'm looking at. I need to encode that geometry into my code. Now when I come downstairs, all the y values are negative, so all my x dot values will be negative. And all of my y dot values, well, with y being negative, when I'm in the fourth quadrant, x is positive, I have a negative number minus a positive number. X should, right, these should go down. When I'm in the third quadrant, y is still negative, x is negative, but this would make a positive term out here. These should start turning up. And so in my MATLAB code, I'm losing information from the arctangent. Well, arctangent and tan, right? Let me get this right. Tangent has a sign on the top of it, so the tangent of negative theta is equal to the negative tangent of theta. So I've got to parse a negative sign through everything that comes out. That's harder to code than we think. But we can do it, and you can use that code to do this. So what I want to do then is I want something that takes care of the sign for me. But notice it was all based off of the y value sign. So y divided by the absolute value of y times the cosine. And y divided by the absolute value of y times the sine. Well, if y is negative 4 divided by the absolute value of negative 4 will be negative 1. If y is positive 4 divided by the absolute value of 4 will be 1. And so this function here does the job of translating our sign information for us and helping take care of our vectors. And so if we come back over here, I now have relatively well-sized vectors that are pointing in the right direction. And we now have working code where no matter what spring function or second order differential function that I give you, you can plot the stream plots. And so we can imagine starting at some initial condition here, and you would spiral inwards, because the drag function would eventually cause it to no longer accelerate, no longer have a velocity, and it would end up terminating in the center. So let's look at just a small change here. Let's turn this into our regular spring function. In fact, let's make it a spring function with a large mass. So no damping. And so now I have a stream plot that if I follow the trajectory, right, it's a heavy mass, so it's taking the spring a lot of work to turn it around. But once it turns around, it comes down on a trajectory. Well, let's try to follow a trajectory out here. Let's get one close. Turns up, over, and so we get circles around a center because it's in equilibrium. And you notice the division by zero issue we have with the way we set up tangents. All right, well, let's do another change here and see what we can get from this function. All right, where did my MATLAB go? There we go. So let's come here and do another change for this. So let's give it a large spring force and a low mass. And now we can see the rotations, and it's very quickly changing. Right? This is the velocity changes; they're happening quickly, but it's circular. Right? There's none of these vectors are coming back. Well, let's try to change some of our parameters and get a better view on this here. So back into here. Well, since we talk about things in terms of pi, I'm going to make this 6.3 to 6.3. Alright, so we're slightly over 2 pi. And see if that doesn't crush things a bit here. My mesh sizes are 0.25. I want to see if I can make a multiplier of 3/4 in the front. Those vectors looked a little big. I'll see if this works. I always hate doing multipliers in here because they can really change it dramatically. But we'll see if we get a good. So let's try that. See if we can shorten the arrows a bit. I'm not sure if that ran. And let me bring the spring constant down a bit. And so there's what I've got. I've got a definite spring. I can see the grid that it's on out to 2 pi. I've got the rotation nature of it. And we're not quite seeing some spiral nature of things, but we can now start exploring differential equations. And we can start really encoding any second order differential equation we see and talk about the parameters that are happening for it. And we can talk about them in terms of streams. So this is the sample code. They'll get us started on doing second order differential equations. So, right. And we can even start adding functions as long as we make sure that we apply that function of f. And I think that's going to be our next game here, is what can we do with the functions of f. So if I bring and redefine f down below, we'll be able to give it a driving function, something that's driving the spring, and see what the solutions look like. For right now, we have the beginning as what is called a phase plot that shows how the system is changing, and we're specifically looking at what's happening at each point on the grid between the x and y values. And the x value is position, and the y value is velocity. The next video I'm going to do, we're going to look at plotting out oscillation graphs so that we can have things coming through. So what I'm hoping to do in the next one. Let me get my Krita up here. Scroll this down. Oh, let me to clear things here. That's good. All right. So what I want to try to do then is I want to be able to take. Let me see if I can get this up here. I want to take x dot equals y, y dot equals f over m minus bm y minus kmx. And we want to take these and plot them for any family of solutions that we might have. And so what we're going to try to do is come up with, because this is our positional value, this is the typical spring value you see. But when we get the typical position right on this, and we get this right change, this is a velocity term. And so the graphs that I want to be able to do is we're going to be able to do time versus position, time versus velocity, which in our thing is y, and then time versus y dot, which is acceleration, which is we've been seeing as sinusoidal waves. Well, now we're going to be able to see damping effects, we'll be able to see moving effects as we're able to work with the different forms of the differential equation as it comes about. So, well, this is kind of not what I wanted. I'll fix it in the future because I've got like the red glowy face. I mean, this is the 8th circle of hell type thing. But what we'll be able to do is, now that we have our driving differential functions, we can use Euler's method on one at a time. I can get all of my velocity updates here, and then I come down here and I take the new velocity and I update my acceleration, right? And then in updating the acceleration, I can get the plots through here. So we'll turn these into the traditional plot we're seeing. But we're also going to see that the stream plots are going to be able to tell us what's going on. And the stream plot will be amazingly useful for us. So play with this, start getting your plots going, and you should be able to start some of the computational things.